Before studying valence bond theory, firstly I am going to present some common terms that are related with valence bond theory. So first is what is coordination compound, then what is central metal ion and ligand, and then the points of valence bond theory. So today I will be covering all these 7 key points. So first is what is coordination compound. Coordination compounds are the molecular compounds which retain their identities even when dissolved in water or in any other solvent. Here is a picture of Alfred Werner. He was awarded by Nobel Prize and rightly called as the father of modern coordination chemistry. The example of coordination compound is hexamine nickel chloride. Next. Now what is central metal ion? Central metal ions are the positive ions which has 2 or more neutral molecules attached to it in a complex compound. Now what is ligand? The molecules or group attached to the central metal ion by a coordinate bonding called as ligands. The ligands may be strong, average or weak in nature. Next. So now the types of ligand. First is the unidentate ligand. This ligand form only with a one donor atom. Now bidentate ligand. This ligand form with a two donor atom. Tridentate ligand and hexadentate ligand. This ligand form with a 3 and 6 donor atom. And last is the unidentate ligand. Last is the chelating ligands. These ligands are the multidentate ligands and they are strong in nature as compared to other. Next. So now our today's topic, that is introduction of valence bond theory. Linus Pauling was an American scientist who introduced this theory in 1931. Hence this theory is also known as Pauling theory. Next please. Now the assumptions of valence bond theory. Coordination compound contain metal ion in which ligands form a coordinate bond to the metal. Ligand must have a lone pair of electrons. Strong bonds are not formed by pure S, pure P and pure D orbitals. Strong bonds are generally formed by the suitable combinations of orbitals. For example, 1s and 3p orbitals form 4sp3 equivalent orbital with the equal energy. This shows the sp3 hybridization. Next. The non-bonding metal electrons occupy the inner d orbitals which do not participate in the hybridization. In the complex formation, Hund's rules of maximum multiplicity strictly follow. However, the redistribution of electrons takes place. In this way, some orbitals are vacated and made available for the hybridization. The number of unpaired electrons in the complexes gives the geometry. When the complex contains any unpaired electron, then they are called as paramagnetic. And when the complex do not contain any unpaired electron, it is called as diamagnetic. Next. Hybridization and geometry. Hybridization is also an expansion of valence bond theory. In this given table, coordination number, hybridization and geometry is given. Next. It is the molecular geometry. Next. Now, example. Our first example is tetracyclonickelate. Here, nickel is our central metal ion. So, first we will write the electronic configuration of nickel. That is Ar 3d8 4s2 4p0. Now, we will write the electronic configuration of nickel with a +2 oxidation state. That is Ar 3d8 4s0 4p0. As the Cn is our strong ligand, it approaches the metal ion. The inner electron present in the metal ion suffers from repulsion. Due to the repulsion experienced by incoming electrons from 4 cyanide ligands, they get paired and form dsp2 hybrid orbitals, each of which accept the ions from cyanide and form NiCN4 2- complex. This complex will be square tetrahedral shape. It do not contain any unpaired electron, so it is diamagnetic in nature. Next, our second example is hexamine chromium. Here chromium is our central metal ion. So first we will write the electronic configuration of chromium, that is Ar 3d5 4s1. Now we will write the electronic configuration of chromium with a +3 oxidation state, that is Ar 3d3 4s0. Here 3p orbital is completely filled, so they do not take part in the chemical bonding, so they are called as non-bonding orbitals. In this combination, only 3d, 4s and 4p orbitals are involved, so they form 4d2sp3 hybrid orbital, each of which accept the electron from 6 amine and form a complex CrNH3/6 This complex is octahedral in shape. It contains 3 unpaired electrons, so it is paramagnetic in nature. Now, magnetic moment. Theoretically, the number of unpaired electrons and magnetic moment will be calculated by a single formula. That is mu is equal to √n of n plus 2. where mu is the magnetic moment, n is the number of unpaired electrons in the spaces, and Bm is the Bohr magneton, which is the unit of magnetic moment. Next, this formula can show the given number of unpaired electrons in the ion are as follows. When we have a one unpaired electron, its magnetic moment will be 1.73. When we have a two unpaired electrons, its magnetic moment will be 2.83. And when we have a 5 unpaired electrons, its magnetic moment will be 5.92. Next. So here are the limitations of valence bond theory. This theory is unable to explain some facts. They are as follows. First, it offers no possibility of predicting magnetic behavior except the number of unpaired electrons in the complexes. Second, the complex formation in the central metal ion is totally unsatisfactory. Third, this theory does not explain why a particular structure is preferred. Fourth, this theory offers no convincing explanation of cause of maximum theory. Fifth,